Okay, all right. So let us start today's session. Mohan Chidambaram, are you able to see the screen? Chidambaram, are you able to see the screen? Okay, thank you, Chidambaram. So, a very good evening to everyone. So now today we are going to discuss the live session number 8. And in the last tutorial session, we have discussed the MPPT algorithms. In that we have seen differential method, and then we have seen this power slope method and hill climbing method. Now in today's session, we are going to see the PV battery interface. So let us, as usual, we will first revise all the contents for the BCAT, and then we will solve some problems. So beginning with beginning with this first slide. So in today's session, we are going to discuss these 4 important parts for PV battery interfaces. The first one is the charge controller, and then we will see the battery charging, and then we will see batteries in series and the charge equalization concept, and then we will see batteries in parallel. So the first question comes that can we directly connect the PV to battery to with this PV? So is this possible that we can connect a battery with this PV? To find that answer, let us first consider the battery model. So let us this battery voltage with VV and this internal resistance of battery. So during charging, if you charge the battery, then what is this equivalent expression? So we are finding the battery model, and then with this IV curve of battery, we will superimpose with this IV characteristics of this PV module. Then we will see that how it is feasible to directly connect battery with the PV. So here, if you see this during charging condition, then this terminal voltage of battery will be VV plus IV RV. And this RV the internal resistance of battery, and we know that this is dynamic in nature and it usually varies with this state of charge of battery. And in contrary, during discharging condition, this current direction will reverse. So how we will write the terminal voltage of battery? This terminal voltage of battery will written like VV minus IV into RV. So this direction of current is very important while charging and discharging. That will decide the terminal voltage of battery. So with the use of these two expression, we will draw this IV characteristics for this battery. So let us first see this IV characteristic for ideal charging. Means in that case, we have considered the internal resistance of battery as 0. So it will be just perpendicular to the x-axis. So this terminal voltage of battery will not change because we have considered this internal resistance of battery as 0. So in charging and discharging both cases, this blue curve is same for this ideal battery or ideal charging. Now, if you consider the practical charging in which we have considered the internal resistance of battery, so in that case, during charging condition, this terminal voltage of battery will increase, and this terminal voltage of battery will increase by the quantity IV into RV. So this is, and based on this charging current, this gap will be more. And similarly in discharging condition, this terminal voltage of battery will decrease, and based on the discharging current, this gap will be more. So now, if you see for this charging and discharging, then you can write the equation for this charging and discharging curve. So if you write this Vt is equal to V plus minus RV, this is one is the generalized expression for battery. And then if you write this IV equal to, then you write it in this such a way that you can relate with this a straight line equation, that is y equal to mx plus c, and here m is slope and c is the y-intercept. So here if you see that we have written this IV characteristics of battery in this straight line equation. So the slope of the battery during charging will be 1 upon RB, while in discharging will be minus 1 upon RB. So from this curve, you can also see that while discharging the slope is negative, while charging the slope is positive. And the y-intercept during charging will be negative as it cuts the negative y-axis, and while discharging, it will cut the y-axis in the positive. It will cut the y-axis at positive side. So y-intercept will be positive for discharging, while this y-intercept for charging will be negative. So now what we are going to do is that we are going to superimpose this IV characteristics with this IV characteristics of PV module that we already have, that we already know, that already has been discussed in the class. So here we are going to superimpose the IV characteristics of PV panel and the IV characteristics of battery. So this blue line is this IV characteristics of PV panel. So let us see this this terminal voltage, and let us this battery voltage as VV, and for this ideal charging, for this ideal battery, this will be a straight line, and for this charging condition, let us cut this cut this IV characteristic of PV panel at this point. It is with respect to certain load, so you can write this equivalent 1 upon RT load line. So as this battery will get charged, so it will move in this direction. So now on moving to this direction, this IV curve, IV characteristics of this battery, then it is coming to that region that it is gets nearly fully charged. So in that condition, this will be the equivalent 1 upon RT load line at the near full charge condition. So during this zone, there will either float charge or trickle charge region. Means this battery is almost charged, so you will whatever it is discharging through load, you will just give this trickle charge through the PV panel. So from this IV characteristics of PV panel and IV characteristics of battery, we can see that no extra electronics is needed to connect this PV panel and the battery if this terminal voltage of battery is matched properly with this open circuit voltage of the PV panel. And also this charging current, I here it is represented by I charge, is matched properly with this ampere hour rating of the battery. So if this IV characteristics of PV panel and IV characteristics of battery is matching properly with the characteristics of both the panel and battery, then you can directly interface the PV panel and battery. As here I have written, this battery voltage should match properly with this open circuit voltage. It should be below this open circuit voltage of the battery, and this charging current should match properly with the ampere hour rating of the battery. Now So for this case, let us take one example. So we have considered a lead acid battery with 12 volt nominal voltage and 20 ampere hour is the rating of battery, and C10 is the C rate for the battery. And this battery voltage is 10.8 volt when discharged, and battery voltage is 14.2 volt when charged. So what will be the maximum charging current? So you can find from the ampere hour rating of battery and the C rate. So the maximum charging current will be 20 upon 10. So it will be 2 ampere. So here this IV characteristic of the PV panel is given. The short circuit is given as 2.5 ampere and open circuit voltage 14.5 volt. So now if you make this IV curve for this battery, then you can see that when it is discharged, this battery voltage is 10.8 volt, and based upon this charging current, the line can be drawn. So it will cut this IV curve for the PV panel at this point. So it is the load, it is the corresponding load line at discharge condition. Now when this battery voltage is fully charged in nearly charged region, then this voltage comes out to be 14.2 volt. It is still less than the open circuit voltage of the PV panel. So corresponding this IV curve will be made, and this load line will be made at the near full charge. So from this example, we can see that it is possible that we can directly interface PV panel with battery. So some conditions should be met. This ampere hour rating should be match this charging current of the battery, and this terminal voltage, this battery voltage should match with this open circuit voltage of the PV panel. So if these conditions are met, you can directly interface the battery with the PV panel. Now when this matching is not possible, then what we can use? Then we have to use some then we can use some power tones converter. So suppose if this battery voltage rating is given as nominal battery voltage rating is given as 24 volt, then you can see that this it is not matching with this open circuit voltage of the PV panel. In that case, you have to use some interface between this PV panel and battery. So we can use this power tones converter, DC-DC converter, and by controlling the duty cycle, you can match the IV current, you can match this characteristics of panel and the battery. Means whatever the PV panel is seeing, this characteristics of the battery can change by controlling the duty cycle of this DC-DC converter. So now the question comes that it is not only this battery is connected to the solar module, it has also the load connected to it. Now how we will control this charging of battery? Till here any doubt? If you have any doubt, you can interrupt me. So let us just recap this IV curve for the PV panel. So based on the insulation, we know this IV characteristics of PV panel varies. So this first one is the IC1 and VOC1 is for certain insulation. Now on decreasing the insulation, this IV characteristics come down. So it will be ISC2, and the corresponding open circuit voltage will be VOC2. And again the insulation comes down, then it will be ISC3, corresponding short circuit current, and the corresponding open voltage will be VOC3. So here if you see this maximum power point, if you see this maximum power point, for all these three insulation, it lies in certain band. Because we know that this short circuit current varies linearly with this insulation. and this open circuit voltage varies logarithmically with this solar insolation. So there is large difference in the short circuit current when when the insulation changes, while this open circuit voltage there is very less minimal difference in the open circuit voltage when this insulation changes. So you can see that accordingly this maximum power point would also vary less. So this for MPPT, this operating point is lies for this within this band only for varying the solar insolation. So what are the observations that we got from this IV curve for by varying the solar insolation? We can see this all peak power points lie within this yellow band, and this operating points will showing in this narrow band for the operating the in the maximum power point region. And in order to hover this operating point in this band, direct connection will not work because it will vary based on this charging and charging and discharging of battery. So we need some electronics to manage power flow from this battery to load or PV to battery or PV to load. So what are the logic for this charge controller? So we need to interface some electronics part so that we can operate the PV at MPPT while supplying power to the load and charging the battery. So this electronic circuit we call it a charge controller, and this charge controller's definition is that it steers power flow from PV module between battery and load. And what is the functional logic of this charge controller? If this battery voltage is greater than V max, and we will see what is this V max and V minimum. So if this battery voltage is greater than some maximum voltage, then we have to disconnect battery from the array and connect to load only. It means that our battery is fully charged. It does not need more charge. So you have to disconnect the battery and you have to just discharge the battery. So this first logic is that if this battery voltage goes beyond the some maximum voltage, you need to disconnect the battery and connect to load only. And if this battery voltage is less than some minimum voltage, means that this battery needs charging. Means you cannot extract more power from the battery. So you have to connect to solar array for charging. And suppose if this battery voltage is within this limit, V minimum and V max, then both the solar array and load are connected to the battery. If this battery voltage is within the limit, means the minimum voltage that is corresponding to the discharge condition and maximum voltage that is corresponding to nearly charged condition. If it is within this region, then you can take the power from solar array for charging, and you can also deliver the power to the load for discharging. So the last condition, so the last logic is that you can simultaneously charge the battery from PV module and discharge through the load. So what is this Vmin and Vmax? So Vmin and Vmax is this band, such that your PV is operating in this MPPT region. So how you will implement this logic to this PV, battery and load, all three are present. So we will see all three cases. So the first case is that when this battery voltage is more than this Vmax voltage, then in that case it means that our battery is fully charged, is nearly fully charged. So you have to just discharge the battery by connecting this, by switching on this S2, and you will discharge the battery through this load. And now let us see the second case. When this battery is less than V minimum voltage, it means that our battery is nearly discharged. Our battery is nearly going to discharge, fully discharged. So we have to disconnect the load and connect with the PV panel so that it can be charged through this PV panel. And the last case, when this our battery voltage is within this region, Vmax, in that case, you can take power from this solar panel for charging, and you can also provide power to the load for discharging. So here, if you observe, the second case is quite is not how you can say, from the customer point of view, it is not a good option. Why it is not good option? Because here you can see this our load is disconnected from the supply. So how this load will get supply from the source? So in order to get power from the source, we have to use one extra switch S3 such that it can be directly connected to this PV panel. So you can extract the power from the PV panel, and this load can operate. So, and if S3 is used, then this battery should not provide power to this load. So in order to make S3 on, in that time we have to make sure that S1 is the induction switch. And this one is the not that much how you can say, is not that much uh, mm, uh, is always is always present is always how you can say. So in most charge controller only S1 S2 present, while S3 is not put, to keep it simple, because it not quietly we face in real scenario. So since mostly we will having in yellow band region, mode 3 in play most of the time, and S1 S2 are sufficient. So here it is telling that this S3 is not necessarily we can use, because this is not one of the commonly encountered uh, example commonly encountered case. So anyone can verify, are you able to see the slide?
Yes, we can see.
Okay, Ramesh, thank you. So this is the logic for the charge controller. If you have solar PV panel, battery, and the load. So now how we will apply this logic? So to apply this logic, either you use the analog implementation or digital implementation. So in the course, the professor has discussed the analog implementation. So for analog implementation, we are taking this switch S1 and S2 as normally closed type. And when this relay coil gets energized, then it gets open. So NC means normally closed type relay, normally closed type switch. So if it does not get any signal, then it will close, and if it gets signal, then it will be open. So how it will work? So we are having this connected to this BJT, and then we are having this transistor, and then we are having this op-amp comparator, and then we are having this buffer, and then we are having this resistor and Zener diode. As Zener diode is used to set this maximum limit. So suppose this and why we are using this buffer? We are using this buffer to avoid the loading effect. So whatever this effect of this resistance should not counter this other part of the circuit. So in order to isolate or in order to avoid the loading effect, we are using this buffer. So only the signal part should come to the other side. It's the other side should not affected by the current and voltage. present at the opposite side of the buffer. So this VV and VV max will come at this side, and with this comparator, suppose if this battery voltage is greater than V max. If this battery voltage is greater than V max, then this gets turned on. This transistor gets turned on, and our relay will get energized. So it will open the switch. Why it open the switch? Because our battery is nearly fully charged. So that's why in this case it will open this switch S1. Similarly, in the opposite side, we can use the same circuit. So this VV here we are getting, you can get directly from this circuit, from this part. And VV minimum is getting from this Zener diode, and with this buffer is to avoid the loading effect. And again we are having the op-amp is used to compare this input, and accordingly you will get the signal to trip this switch. So here at the left side you can see this V max is connected to negative terminal, while on the right side V min is connected to this positive terminal of op-amp. So if this V battery voltage is less than minimum voltage, means our battery is nearly discharged, is nearly at the fully discharged condition. So our switch should be disconnected from the load. So this VV comes here, and this V minimum, and if this VV will be less than V minimum, so it gets turned on, our transistor gets turned on, and this relay will open this switch S2. So in that way, we can imply this logic for charge controller. And for the rest of the case, means our battery voltage if lies between this V max and V minimum, both the switches should be closed. So that is the normal condition. During normal condition, both switch S1 and S2 are closed. One minute. Anyone has doubt how to calculate hysteresis value in volt? We will see some problems based on this hysteresis op-amp for this comparator type Schmitt triggered circuit. I have, I think, one or two problems based on this Schmitt triggered circuit. So let us come to this next part. So now this battery charging part. So here we will see this current control. So what we are knowing that this battery voltage, this output voltage of this converter is fixed through this battery. So we have to control this current I naught. So how we are going to control this current? So in other way, you can say that you can you cannot control this voltage, because if you put this at the if you put source on the left side, that is as a voltage source, that you cannot directly connect two voltage source in parallel. There will be huge circulating current flow between these two voltage source. So in order to control, we have to put some series impedances so that you can limit the current. So this is not a good option. Other way is that you can have this voltage source and you can connect this series inductive impedance that can work as a current source, and you can charge the battery. So this in this left side, if you just take it as this current source, then it has characteristics of inbuilt impedance so that it can limit the current. Now we will see one power to converter based battery charger, current control battery charger. In that we have used this buck converter. So here we have this PV panel, and then we are having this buck converter, and this battery is connected at the output of this converter, and load is also connected at the terminal of battery. So how you will this control this converter such that our battery gets charged. So what is the logic? So this one is the logic. You have to provide some difference value, IL difference, that is the output current of the converter, and then you have to sense this output current of the converter IL, and you uh, compare it, and you just provide it with this op amp or with this comparator, and then you have to provide this SR latch, and this based on this SR latch, it will provide this output of SR latch will provide the signal to turn on or turn off the switch. And how we are deciding this switching frequency of this converter? We have to use this clock, and this this from this clock we are providing the pulses in a such a way that um, between two pulses there is this switching that decide the switching time for this converter. So suppose you are having this IL difference, and if this IL difference is less than IL, so let us see the first case. So first case, let us check is that IL difference greater than IL. So it will be positive value. So it is high. And if it is passed through this comparator, then it will give the low. Low means it will having zero value. So if it is zero value, then this Q signal will remain as it is at the previous state. So this Q signal will remain as it the previous state. Q will be in previous state. Now, if we take the another case, in that case, if you take this IL difference is less than IL, then it is having negative value. So if it is negative value, that means you can consider a low. So this zero, this plus VCC will come at the output of comparator. So it will be high. So if this high signal is going to R input of SR latch, then you can see the truth table of SR latch. So this was for the previous case, and the next case is 0, 1. So it will reset the output. So here we will get the reset value, that means you will get 0. So at that point you have to turn off the switch. So in this logic, this converter is operating. So if you see here, this inductor gets charged, when this IL difference is greater than IL, and once this inductor current wants to increase value beyond this IL difference, then it reset this flip flop, and this it provide the pulse, it turned off the switch, so our inductor gets discharged. So this is the signal that we are getting from the Q flip flop, and this is the logic for current controlled battery charger based on this buck converter. So this is quite simple. Means if this IL difference is greater than inductor current, our inductor gets charged, and when it wants to increase its value more than IL difference, our SR latch output gets 0, such that this switch Q gets turned off, and it is going to discharge, and again it gets signal from this clock, so it sets the value and it turn on the switch, and if it gets want to increase the value beyond this IL difference, then again SR flip flop reset its value and it turned off the switch Q. So it gets the switch Q gets turned off, and this inductor gets discharge through this battery or load. So this is the buck converter based current control battery charger. Any doubt here till here? What is the maximum duty cycle can be achieved by this work? So we are going to see in the next part. So what happens is that the maximum duty cycle that we are going to achieve is at 0.5. Beyond that, if some disturbance come, then our system gets unstable. So our system gets unstable. So what is the issue? So our if duty cycle is less than 0.5, and this blue curve, if you see here, this blue point is the inductor current without disturbances. So it blends smoothly, and now if there is some disturbance comes in the converter, then this starts from the different value. Suppose it starts with a different value and it is in parallel with this previous inductor value. So if you see, it goes here, and again by getting the signal from the charge controller, it gets switched off and it becomes here, and by getting signal from the clock, it gets turned on again, so it comes here. So if you see if you see the curve here, you can see that in 2 or 3 cycle it gets stabilized, it gets come back, it overlap with the previous inductor current where there is no disturbances. While if this duty ratio is greater than 0.5, then what happens is that this discharging period becomes less, and if this discharging period is less, then that is problematic for this converter to get stabilized. And you can see from this diagram, this blue curve is for this inductor current without disturbance, and this purple color is for the disturbances. So if you see this, our some disturbances will create the inductor current to start from here, and it gets charged till here, and after that it wants to get over the IL difference value. So this controller will switch off the circuit, and this the inductor will get discharged. Again, this clock will provide the signal to get turned on the switch. So it will just charge to this region, and again it wants to go above this IL difference. So this controller will provide the signal to get turned off the switch. So it goes to this point, and because it will get signal from the clock to get charged, after that only it gets a start to charged if you turn on the switch. So this will follow till here, and it is all the lines should be parallel to this previous inductor current. That is very important. So you can see that it gets more unstable condition, and you will never get a stable system. So that is the problem when this duty cycle is greater than 0.5 for this current charge controller. Now, what is the solution for this problem? So in spite of this IL difference, we have to provide some other reference value, other inductor current reference, other output current reference, such that our system gets stabilized quickly. So that solution we called it as slope compensation. So on the previous this output current reference, inductor current reference we are providing is this green line, that is fixed IL difference, and the new IL difference we are providing is this sky blue color. So it is sawtooth waveform. So how we can design this sawtooth waveform? So as a layman, you have to put this slope of sawtooth equal to this falling slope of the inductor current, and you can easily find this falling slope of the inductor current. That slope comes as from this turned off condition of the switch. So we will see one problem based on this also, how we can find this slope of sawtooth. The slope of sawtooth is equal to falling slope of the current, and this inductor current expression we easily know during turn on and turn off condition. And during turn off condition, the whatever the value we are getting for the inductor current, from there we will find the falling slope of the inductor current. So here this current control with slope compensation will provide the good results, and the error is removed within cycle and the system becomes stable. So here you can see this earlier one was with this system, where this our system gets unstable, while the new one gets quickly stabilized to this system. If you see here, this inductor, our system get disturbances, so it starts from different inductor value, so it will go till here, and again its gas wants to increase over this IL difference. So our controller will provide turned off the switch, so this inductor current gets discharged. So here this clock will provide the signal to turn on the switch, so it gets our switch provider. So this inductor current gets charged. Again it wants to go above this IL difference, so it is going to discharge. So you can see this in one cycle it gets stabilized. So that is the benefit of slope compensation. And how we will get this curve? That is very easy. You can refer to the class lecture. I have not discussed here. I have put the slide only. So you can see this IL difference, and if you see this I slope, that we call like the falling slope of the inductor current. So this falling slope of inductor current will be output voltage upon L. So this VV is the output voltage, and L is the inductor value. This is falling slope, and you will get the slope compensatory difference by subtracting this I slope from IL difference. So this will be the slope compensatory difference, IL difference minus IL slope, and you provide this switching frequency by deciding this clock. So this is how we generate this waveform. To generate this waveform, we have to use some electronic circuit. So as we know that this VL is equal to L di by dt, and during turn off condition, this inductor current will be minus VV upon L integration dt. So this I slope will be VV upon L into dt, integration of dt. So if you want to emulate this expression, then you have to use some current control, this current source in parallel with this capacitor. So now if you write this equation of this voltage across this capacitor, then it will be 1 upon Cs into I dt. Now if you compare this I upon Cs with this Pauling slope of the inductor current Vv upon L, then you will get this I value. So I value you will get as Vv upon L into Cs upon Cs into dt. So this I value will be Vv into Cs upon L. So based on this current source in parallel with this capacitor, you can emulate this expression, and you have to just provide this clock here. You have to just interface this clock here, and you will get this slope compensator difference from this current source. Disturbance meaning like some load disturbances also, some fault means if you suddenly increase load, or if there is some fault in the circuit. So in that case, the our inductor current will vary abruptly. So coming to the next part, the next part is that here in this circuit we have this MPPT battery charger and this slope compensated current control. So all these things we have studied, all these things are implemented here. So here we are having this IL difference is coming from this MPPT algorithm, and from this slope compensated reference circuit, we are getting this slope compensated reference value, and we are comparing this reference value with inductor current, and this is the charge controller circuit. So this part is the charge controller circuit, and this part is the circuit to generate slope compensated reference current, and this part is for applying the MPPT algorithm for MPPT. So that earlier what we are doing, we are just providing any anonymous IL difference. But if you provide it through MPPT algorithm, then you have to put some MPPT logic that we have seen in the previous session. From there you can get some IL difference, and this IL difference should be compensated with this slope compensated reference based circuit, and you have to pass it through this charge controller circuit. Sorry. So this is current control. This is current controller circuit. So now coming to the next part, where we are going to see the battery in series. So what is the need of connection battery in series? So we can see that it increase the terminal voltage, and it will having this lower current for fixed power that will reduce our power loss. So if you connect this battery, that will increase the terminal voltage. And if all batteries have the same specification, then you can write VV1, VV2, correspondingly VVN equal to VV. So it will be VT equal to N times VV. But practically, all battery don't have this identical voltage, even when they are made from the same manufacturer, because they will accordingly they will charge differently. So in practical case, each battery charge and discharge at different rates. If it is made from the same manufacturer also, uh, there will be some differences in this battery voltage. So so in order to what we have to do something to do the charge balancing. So here we have using this charge equalization circuit. If you connect this battery, um, if you connect some battery in series, then it is not necessary that all this battery voltage have the same voltage level. So in order to make this battery voltage same, we have to use this charge equalization circuit such that to make this charge to be equally distributed to all the batteries, and we can make this battery voltage VV1, VV2 equal to same VV voltage. So here this charge equalization circuit, again we have to use some switch mode DC-DC converter. So usually for this charge equalization circuit, we are going to use this switch mode DC-DC converter. So first we will see this simple charge equalization circuit that is not quietly used. So this is the what is the first case? You just directly connect some fixed resistor value to all these different battery. So what is the disadvantage of this circuit? Disadvantage of this circuit is that it is quite dissipative in nature and it is quite having large power loss, and we can see that this power loss is equal to VV square upon R in each resistor. But the advantage that it is quite robust and it having low component count. And one important point is that here you have to connect shunt resistor in such a way that 1 to 2% of load current flows through the resistor branch. So this is the important for this resistive alternative branch. Now we will see this charge pump based charge equalization circuit that is quite uh, commonly used, and it is commonly known to. So it is this charge pump based charge equalization circuit is based on this switched mode power conversion, and this method is comparatively efficient. We have seen the previous case, it is quite heavy power loss due to this resistor used across this parallel to the battery. So how this charge pump based charge equalizer circuit works? So here we are having this buck boost converter, and this having buck boost converter. So across each battery we are connecting one buck boost converter, and it is connected to the same output capacitor. All these batteries are connected to the same output capacitor. So for easy to understand, we have taken only two batteries. So what it is doing, if you provide this during turn on time, our this inductor get discharged. Means like whenever this battery having higher voltage, then some value, then inductor gets discharged. It means that it is providing excess charge to this inductor. And when this our switch gets during turn of time, if you see that it gets passed to this another battery, it gets passed through this VV2 battery, and it passed through this capacitor, and it close this circuit. So it provides extra charge that they have stored during this turn on time in the inductor. It provides extra charge to the battery or this reservoir capacitor. So during turn on time, the excess charge gets stored in the inductor, and during turn on time, it provides the charge to the other battery or this stored in this reservoir capacitor. Now if we see for another battery, again during turn on time, the excess charge will get stored in this inductor, and during turn of time, it gets stored in the reservoir capacitor. And now if you see that reservoir capacitor, how it will push the excess charge it has stored. So to push the excess charge, we have to use another circuit. So again, we are using this buck boost converter. So again, this one is also buck boost converter. So to push this extra excess charge, so during turn on time, again this inductor gets stored this charge, and during turn off time, this excess charge will go to this battery. So it is pumping the extra charge to this battery. So that's why it is called as charge pump based charge equivalent circuit. So here I have written all these 3 points. This blue circuit, this buck boost converter is used to remove excess charge from VV1 during turn on time and give it to battery 2, and this is wire capacitor during off time. And this green circuit, that is buck boost converter, is used to remove excess charge from this battery voltage from this battery to during turn on time and give it to reservoir capacitor during turn on time. And this red circuit is this pump circuit, this charge pump circuit. So this charge pump circuit is used as charge pump to equally distribute reservoir capacitor energy to this battery 1 and battery 2 during turn on time. See, this reservoir capacitor give its energy to inductor, and during turn on time, this inductor provides energy to battery 1 and battery 2. And for this logic, how we will provide the pulses, here we are having this terminal voltage across all the battery, then this battery connected in series, and you have to distribute by n, so that we will get the voltage that required voltage that should be coming across all the battery. So this is the required voltage that should come across all the battery. So this voltage is the required voltage value that we want. In other way, you can say that this is the reference voltage that we want across each battery. So you have to pass it through this comparator, and if this voltage is less than this present value, then it gets high. So if it gets high, then it provides, if at the time clock is providing pulses, then it gets turned on. So our switch gets turned on. You can say it will also get high. So here, if this voltage is having battery voltage is having higher voltage value is higher than the reference value, our switch gets turned on because we have to remove the excess charge from the battery. So in that way, this logic works. Here, this whatever the voltage coming, that is difference value of Vt upon N. And if this voltage is greater than this battery voltage, it means if the battery voltage is greater than the reference value, it means that you have to remove the excess charge from the battery and it gets stored in the inductor. And during turn off time, it gets stored either in the other battery or in the reservoir capacitor. So coming to the next part, that batteries in parallel. So in the series, if you are connecting the batteries in series, you are increasing the terminal voltage. And if you are connecting the batteries in parallel, it means you are increasing the discharge current capability. And we all know that we cannot connect directly voltage source in parallel. And in practical, we know this. If these batteries are if the batteries are coming from same manufacturer, also they have different voltage levels. So there will be huge circulating current with consequent reduction in capacity. So to avoid problem of circulating current, following connection can be used. Here we have used this diode across the through this battery. So it is a feasible solution? No, it is not the quite good option. So still some current sharing among these two batteries will happen with this circuit and due to the internal resistance of the battery. So this internal resistance of the battery will control this current contribution from these two batteries, and even due to internal resistance of the battery, this uh, uh, this diode may get into reverse biased and one battery may get out of service. So this is not the quite good option to prevent the circulating current. But anyway, this is if you don't have any other advanced option, then you can use this option also. So another good option is that you have to use you have to use some electronic interface while connecting the battery in parallel. So first we will see this indirection power flow. That means you are providing the power from battery to this capacitor or to the load. So here we are connecting the battery. Battery is connected to this node. So let us see this first case where this unidirectional power flow. So how you can connect the battery in parallel. So you have to use this power tuning interface. So here we have used this non-isolated converters. So one simple way is to use this boost converter. So here this voltage level is fixed by changing the duty cycle of this boost converter. And you can also use the isolated converter. It is not necessary that you can have to use non-isolated converter only. So you can also use the non-isolated converter. So using this circuit, power tuning circuit, this power from battery 1 and battery 2 can be provided to the output capacitor CT. An advantage of this power tuning converter is that with this battery voltage 1 and battery voltage 2 are not same, and this voltage is not same, then also using duty cycle control, this output voltage can be kept identical. So this reference value that we provide to all these converters, we have to provide it as same because this voltage is fixed and this uh, battery voltage may be different. So by changing the duty cycle, you can keep the output voltage identical. Now here, what is the problem? Due to this unidirectional power flow, suppose if this R naught is infinite, if this R naught is taking very less current or R naught is very infinite, in that case, our capacitor gets overcharged. It gets overcharged, it may blow up. If it may blow up our electronic circuit, it may blow up our this solar PV, it may blow up our load. So how to prevent it? So for that, we have to use the bidirectional power flow mechanism. So to prevent this overcharged capacitor and to prevent our load and PV panel from this blow up, we have to use bidirectional power flow. So for bidirectional power flow, I think many of you know how we can connect the battery to this solar PV in bidirectional way. To this, for that we have to use this buck boost converter. So during this blue part represents the boost converter. In that part, this power flow from the battery to this capacitor, and this red part that is that if you interface this switch here and this diode here, then it will work as buck converter, and this power will flow from the capacitor to battery. So when we turn on this switch, at that time it is enable syncing, and when we turn on this switch, it enables sourcing. Means it is providing power from the battery to capacitor, and syncing means you are syncing the power from the capacitor to the battery. Means you are charging the battery from the capacitor from the DC link. So this block we can connect many such type of blocks. So you can connect many batteries in parallel. And what is the logic for enable sourcing and enable syncing? So we have set this some terminal voltage maximum, and if this terminal voltage is less than this VT max value, then our comparator gets high value. So this comparator will get high value. That means this input will gets high if this clock signal is high. Then boost operation is on, and this power flow from battery to CT. And again here we will, for syncing condition, we will just provide the opposite signal to the polarity of this op-amp, and in consequent way, if the operation is VT greater than VT max, then our op-amp will get high signal, provide high signal, and this and it will provide a signal, and this provide enable syncing. So backup operation is on, and this power flows from the capacitor to battery. So this is the all the storage part, all the discussion about the current assignment. So let us come to the problem. So we will quickly solve problem. We will not take that much time, and you can also solve problem in parallel with me. So let us see the first problem. So here a boost converter is to charge a battery in a current controlled manner. The boost converter is being supplied by 36 volt PV source. The battery has a nominal voltage of 60 volt. The boost converter uses a MOSFET power semiconductor switch, which is switched at 50 kilowatt. The boost converter uses 4 millimeter with a maximum current of 3 ampere. The slope in the current reference in volts per millihenry is. So how we will solve this problem? So let us first draw the circuit. So a P panel is there, and then we are having this boost converter, and this terminal voltage is given as 36 volt. Terminal voltage of PV is given 36 volt, and boost converter is circuit is like this. And this battery nominal voltage is 60. The boost converter is MOSFET fast voltage, which is switched as 50 kilohertz. So we are providing it 50 kilohertz, and this value is 4 millihenry, and this inductor maximum value is 3 ampere. the slope in the current difference in volts per millihenry is. So we have to find the slope. So how we will make the IL current? Let's make the band first. So during charging, then discharging. So this is IL, this is IL max, this is IL min, and then we have this battery voltage. Sorry, this we have inductor voltage. When during turn on time, this voltage across inductor will be equal to Vt. So it will be Vt, and during turn on time, this inductor voltage will be Vt minus V naught. So you can also make it at V naught. So it will be V naught minus Vt. So the slope of current difference, the slope will be during turn on time will be what? So you can write like this also, VL equal to L di by dt. VL of, we are taking during turn off condition, L di by dt. So VL of is Vt minus V naught L di by dt. So slope will be Vt minus V naught upon L. So Vt is 36 volt and V naught is 60 volt and L is 4 millihenry. So it will give you minus 6 volt per millihenry. So the current slope of current reference in volts per milli minus 6 volt per millihenry, the answer. So today, how many participants are there? So today we have Mohan Chidambaram, Neeraj, Salini, Ramesh, Rajnikant, Chandni, Pavakran, Deepak. So you all try yourself also while I'm solving problem. Today we have less time, so we will little bit go faster. So let us come to the next problem. Here in this problem, solar energy installation is a three-phase line commutated full bridge converter to feed energy in the power system through a transformer of 400 volt, 1:1 as shown below. The energy is collected from PV array in a bank of 4-volt battery. So this is 400 volt battery and connected to converter through a large filter of choke resistance. So this resistance value is 10 ohm. The maximum current for the battery will be. So maximum current to the maximum. So this output will be, if you see this output will be some value, DC value. So it is VDC. This is V battery. So for maximum current, this inductor gets short circuited. So IV equal to, this is, let us take this IV equal to V battery minus VDC upon R. So IB maximum. So IB maximum, to make IB maximum, this DC value should 0. So to get IB maximum, this DC value will be 0. So V battery upon R. So V battery is 400 volt, R is 10 ohm. So it will give you 40 ampere. So 40 ampere is the answer. Now let us see the next problem. So the problem is same. You have to find the kVA rating of the input transformer. So the kVA rating of the input transformer. So we will use this value IB max we have found as 40 ampere. So this IB max is coming as 40 ampere. So we have to find the source current RMS first. So IS RMS we will get equal to √2 upon √3 I battery. So how it is coming? So we have to go to this undergrad course. There we having control rectifier. So if you are having control rectifier, then this ISCT heat supply conducts for 240 degree. So heat supply conducts for 240 degrees. So this is I naught. This is for 120 degree. Again for 120 degree. This is minus I naught. So IS average will be 0. And this IS RMS will be I naught upon 240 upon 360. So it will coming as I naught into root upon 3. So IS RMS will be root 2 upon 3. I battery is 40. Therefore, VA rating will be, VA rating of input transformer will be √3 VS into IS. So VS is given as 400 volt into root upon 3 into 40. So it will give you 22.6 kV. So 2.6 kV. This is the answer. Now let us see the next problem. So here the flowing circuitry can be used in the battery charge controller to reduce shattering and proper operation of the mechanical relays used for switching. The transfer characteristic of the circuit will be. So what is the transfer characteristics? So you have to make the waveform. So what is the, so let us apply superposition. So let us assume this as V1 voltage, here V2 voltage. This will be the V3 voltage. So what should be the V3 voltage? V3 voltage. Let us first take the first case V1. So V1 is at the negative terminals. So it is minus R upon R into V1. So this is for first part. Now for voltage V2, so we have to 1 plus R upon R, 1 plus R upon R. So this part, and then we have to provide this V plus. So then here V plus will be V2 into R plus R. So it will be V2 upon 2. So here 1 plus R upon R into V2 by 2. So this will be V3 equal to minus V1 and plus V2. So you can write V3 equal to minus V in. Now for second part, for this part here we can see that this is positive feedback. So if this positive feedback, then it acts as a Smith trigger circuit. So it acts as a comparator. So it acts as a comparator. So how you make the output of comparator? So this output of a comparator will give the output as hysteresis. So it is hysteresis op-amp. So first let us take this output voltage as plus VCC. Let us take this output voltage as plus VCC. That means 12 volt. So if you assume this V0 plus 12 volt, let us take this one case. If V3 is greater than is less than 6 volt. So if V3 is less than 6 volt, if you assume this V0 as 12 volt, then it will come as 6 volt. So if V3 is less than 6 volt, then output will be plus VCC. So V0 will be plus VCC. And if V3 is greater than 6 volt, this output will be minus VCC. Now take the assume V0 equal to minus VCC, that means minus 12 volt. So in that case, it will be minus 6 volt. So in that case, it will be minus 6 volt. So if V3 is less than minus 6 volt, if it is less than minus 6 volt, then V0 will be plus VCC. So V0 is plus VCC, and if V3 greater than minus 6 volt, V0 is minus VCC. Therefore, we can make the output of this circuit so let us first take this 6 volt, and so V3, if input is greater than 6 volt, if input greater than 6 volt, then we are getting the plus VCC. Sorry, if input is less than 6 volt, then we are getting the plus VCC. That means this way. If input is less than 6 volt, then we are getting the plus VCC, and input is greater than 6 volt, then we are getting minus VCC. So circuit will come like this, and it will go this one. So this will be plus VCC. Plus VCC means 12 volt. it will go like this and it will go like this. Now for minus 6 volt, let us represent this as minus 6. So if V3 is less than minus 6 volt in this way, so V0 is plus VCC. V0 is plus VCC. So it will be this one. So V3 is less than minus 6 volt. This will be plus 6 volt, and if V3 is greater than minus 6 volt, that means this way it will be minus VCC. So it will be like this. Complete circuit will like this. So here we have made this respect to V3. So how we will make this with respect to V in? So we know that V in equal to minus V3. So V in equal to minus V3. So just we have to flip the axis. You have to flip across the y axis. So minus 6 plus 6, 12 minus 12. So this will be with respect to V0 and V in. So in the previous case, this is clockwise direction. Now, since V in is equal to minus V3, this will be in anti-clockwise direction. So this is the correct answer. Now let us see the next problem. So the flowing circuitry is used to yes, I have some. You can load also problem. You can upload also problem. Yes, I will upload also problem. This circuit will it bursts with 0 to 12 volt or to eliminate requirement of bipolar power supply. Which circuit you are talking about, Chidambaram? Yes, this circuit will work. This entire range is given. Means I have made this output voltage basis input voltage. So if you having the greater means if your voltage level is greater than 6 volt, then output voltage is 12 volt. And if your voltage level is less than 6 minus 6 volt, then output voltage will be minus 12 volt. And how this within 6 and 6 volt this hysteresis loop be formed. So let us see the next problem. The flowing circuitry is used mathematical operation in a battery charge equalization. The operation is being implemented using circuitry. So I just request all of you please solve and type your answer in the chat box. So this is quite simple one. So here we will apply the KCL. So let us take this as x-axis, x point. Let us take this x point. So add node x. So add node x. So this will be the V2 voltage using virtual ground. This will be the V2 the voltage, and this one is the V1 voltage. So add node x. If you apply KCL, then no current will flow inside the op-amp. So it will be across 2R will be V2 minus V1 2R, and so let us assume this way. So we are assuming the current direction this way, V1 minus V2 upon 2R plus V2 minus, so let us take this as voltage V3 and this voltage as V4. So V2 minus V3 upon R equal to 0. So if you solve, sorry, this will be equal. So if you solve, then equally V3 equal to 3 V2 minus V1 upon 2. So we got this V3 voltage in terms of V1 and V2. Now similarly we can apply KCL at node Y. KCL at node Y, then KCL at node Y, then V2 minus V1 upon 2R equal to V1 minus V4 upon R. On solving, you will get V4 as 3 V1 minus V2 upon 2. So we got V3 and V4 voltage. Now so V0 voltage is quite simple. So V0 voltage will be minus R upon R into V3, and this voltage will be V4 upon 2. So here the expression will be 1 plus R plus R into V4 upon 2. So V4 upon 2R. It's okay. V4 upon 2. So you will get minus V3 plus V4. So V0 will be 2V1 minus 2V2. So V0 equal to 2 into V1 minus V2. So this is the correct answer. So which option is matching? A option is correct. Yes, Rajnikant, correct. A option is correct. Now let us see the next problem. So this problem, 5 batteries, each of 12-volt terminal are connected in series. A charge pump based equalization circuit is employed. The reservoir capacitor voltage can be. Five batteries, each of 12-volt terminal are connected in series. A charge pump circuit is employed. The reservoir capacitor voltage can be. So if we see this charge based equalization circuit, then this side we are having battery bank. So, if the nominal voltage twelve into 5 equal to 60 volt. So this input voltage should be less than V nominal voltage. And this is the output of boost converter. So nominal voltage of battery is output of boost converter. So one option is matching with this circuit. Only C option is correct, 48 volt. So this therefore is satisfied, that is 48 volt. Therefore reservoir capacitor voltage is 48 volt. Now let us see the next problem. A lead acid battery and lithium polymer battery are supposed to supply current to common load. Then one should connect the batteries in series, one should connect the batteries in parallel, one should not use batteries of different types, one should use charge equalizers. What do you think? So there are two different batteries. So you cannot connect two batteries in series. So one should connect the batteries in parallel. So B option is correct. Now let us see the next problem. The 20 ampere hour battery with a nominal voltage of 12 volt is connected to the terminal of PV module. PV module for charging. The PV module has short circuit current 2.5 ampere and open circuit voltage of 14.5 voltage. The battery has C rate of C by 10. If the internal station battery is quantum, the appropriate operating point will be. So it is quite simple problem. So here we are having given with this PV with all the data, and then it is connected directly with internal resist with the battery. So this ampere hour rating is 20 ampere hour, and battery nominal voltage is given as 12 volt and C rate is C by 10. So this charging current will be 20 ampere hour upon 10. So it will be 2 ampere. So I will be 2 ampere. Now for the PV module, this short circuit current is given as 2.5 ampere and open circuit voltage given as 14.5 volt. The internal resistance is given as 0.5 ohm. The appropriate operating point will be. So let us take this as voltage VT. So just apply KVL here. So VT minus 0.5 I minus 12 equal to 0. So you can take this charging current. So ICHG. So VT minus 0.5 into 2 minus 12 equal to 0. So VT will be 13 volt. So operating point is VT comma I. So VT is 13 volt and current is 2 ampere. So correct answer is C. Now let us see the next problem. It is same problem. You have to find then the approximate input resistance seen by the PV module. So input resistance seen by the PV module is RT equal to VT upon I is charging. So VT is 13 volt, charging current is 2. So input resistance seen by the PV module is 6.5 ohm. So A is the correct answer. Now, so from the question 6, the so I think it again is some mistake. So let us escape. There is some mistake in this problem. It is from the previous session. So let us come to the next problem, question 11. The current control buck converter is operating at a duty ratio of D without slope combustion. Due to a transient in the load current, a disturbance is induced in the inductor current. Which of the following statements are correct? So we know that we can write one line here without slope compensation for current controlled buck converter it becomes unstable above 0.5 duty ratio. So first one is unstable if duty ratio is 0.5, it is incorrect. Stable if duty ratio is greater than 5, it is incorrect. Stable if duty ratio is 0.4, it is correct. Unstable if duty ratio is 0.7, it is correct. Unstable if duty ratio is 0.1, it is incorrect. So unstable if duty ratio is 0.15. So it is multiple select question. More than one options are correct. So options are C, D, and F. Let us see the next problem. The maximum duty ratio of current control to operate with slope compensation to operate in a stable condition. So maximum duty ratio can be maximum duty ratio can be 1 because you have used the slope compensation method. So let us see the next problem. The input voltage to a boost converter is 24 volt. The duty ratio of the converter for supplying load of 5 ampere at 48 voltage. That is quite simple one. Boost converter is there. So we know that relation between for boost converter V naught equal to V in upon 1 minus D. So output voltage given as 48 volt, input is given as 24. So if to find the duty ratio, the duty ratio is 0.5. 0.5 is the correct answer. Next problem is that a 12 volt lead acid battery is charging is charging directly through a PV panel at a certain point of operation. The battery had an open circuit voltage of 11 volt and the PV panel was operating 13 volt terminal voltage while delivering 2 ampere of current. Then what was the internal resistance of the battery at that point? So internal resistance is the slope of battery profile. So internal resistance of the battery is the slope of battery profile. So internal resistance will be 13 is the terminal voltage PV panel and 11 volt is the battery open circuit voltage and current is flowing 2 ampere divided by 2. So it will be 1 ohm. So next part, a buck converter is charging a battery of voltage VV using a current control. The input of the buck converter is fed from a source of voltage V in. If the buck converter has inductor of value L, then what is the magnitude slope inductor when the power switch is on? So we all know that buck converter configuration. So this one is like this. So during on condition, if you make it on, so here if you provide input, output, so during on condition, this will be reverse biased. So VL on will be V in minus V naught. So L di by dt equal to V in minus V naught. So slope equal to dIL upon dt. So V in minus V naught upon L. So the correct answer is, so here V naught is battery voltage. So correct answer is D. Let us see the next problem. So a buck converter is used to charge a battery during charge current. The buck converter being supplied a PV source with terminal voltage of 20 volt. The battery is nominal voltage of 9 volt. The buck converter is MOSFET power semiconductor. So input voltage 20 volt, output voltage 9 volt. The buck converter is MOSFET semiconductor switch, which is switched at 50 kHz frequency. The buck converter is 3 millihenry inductor. What is the magnitude of slope of the start current difference? So we know that the slope during turn up condition will be battery voltage upon L. So battery voltage is 9, L is 3 millihenry. So 9 volt per millihenry. 9 volt per 3 millihenry. So it will be 3000 volt per henry. So but they are asking in ampere per second. So it is the unit will be same, 3000 ampere per second. How it is coming ampere per second? So if we want to get in amperes per second, then what you can use? So from here you can get EMF equation is minus L d upon dt. So this is volt, this is Henry, and this is ampere per second. So volt per Henry equal to ampere per second. So the both unit are same. So 3000 per ampere per second is the correct answer. Now let us see the next problem. Consider a battery that is modeled as a current constant voltage source with 30 volt in series with 2 ohm. The battery is charging resistive to then the terminal voltage of battery will be. So it is also very simple. Load is 5 ohm, internal resistance is 2 ohm. It is asked that terminal voltage of battery. So terminal voltage of battery will be 30 minus current will be 30 upon 7 into 2. So it will be 30 minus 8.57143. So it is 21.428 volt. So it is 21.43 volt. Let us see the next problem. Two batteries connected parallel. Each battery is modeled at constant voltage in series with internal resistance given. The tail of each battery voltage given. The magnitude of circulating current flowing through a parallel combination. Circulating current will be VV1 minus VV2 VV1 minus VV2 upon RS1 plus RS2. So 20 minus 15. So it is VV2. 20 minus 50 upon 0.7. So it is 7.1428 ohm, approximately equal to 7.143 ampere. The duty ratio HV buck boost converter has to operate in order to have the same magnitude of rising and falling slope in the inductor current. So the correct answer is 0.5. How we will get this boost converter? So let us first make the buck converter configuration. Buck converter configuration is like this. So buck converter buck is like this, and in buck boost converter we have to exchange this one. So buck boost converter will be like this with opposite output polarity. So this is for buck boost converter. So during turn on time, during turn on VL is equal to V in. So from here slope will become as di upon dt V in upon L, while during turn of time this output voltage will come. So di upon dt equal to slope equal to V naught upon L, and we know that the relation between output and input voltage V naught equal to V in into d upon 1 minus t. So V naught equal to V in comes when dt equal to 0.5. So in that case, both slope will become equal. So this slope and this slope will become equal. So 0.5 is the correct answer. Now let us see the next problem. Referring to the previous question, what will magnitude of output voltage converter during the DC ratio? Assume the converter will supply with DC voltage of 100 volt. So all of you once try. Here it is asking about magnitude voltage. So you don't need to take the minus sign. So V in D upon 1 minus D. So input voltage given as 100 volt. Duty ratio is 0.5. So output voltage will be 0.100 volt. Let us see the next problem. So a battery with a 12 volt nominal voltage is connected directly to the PV module. The terminal voltage measured at the PV terminal is 11 volt at battery source 20% and 13.5 volt at battery 100%. This IV is shown below. The watt resistance is measured from the PV of terminals at operating point C. On its IV characteristic, consider the curve between the operating point C and V is approximate to a straight line. The current relation is IC is equal to this one. So how we will approach this problem? So we are having this PV panel connected with this battery. This nominal voltage is given as 12 volt and this terminal voltage is given as 11 volt at SOC of 20%. And this terminal voltage given as 13.5 volt at SOC of 100%. So let us take this as terminal voltage. So we have to find the resistance in ohm at operating point C. All right. So first let us find the slope, then we can find the resistance very easily. So the first point, if you see this A point is correlated with X is 11 and Y is 18. While B point, it is 13.5, 5. Then you can directly write you have 2 points 11, 18 and 13.5, 5. So you can directly write the straight line equation y minus 18 equal to y2 minus y1 upon x2 minus x1 into x minus 11. So if you solve this, you will get y equal to minus 5.4x plus 77.4. So this is the straight line equation you will get. So you can write in the terms of IPV minus 5.4 VPV plus 77.4. So now we have to find the IPVC, VPVC. IPVC is given as 9. How we will got this IC? I represented IPVC 9.2. So we will get from this one. So IPVC equal to 0.4. IA is given as 18 and I will given as 5. So it will be coming as 9.2. So to just put this value, so you will get 9.2 minus 5.4 VPVC plus 77.4. So VPVC will be 12.63 volt. Therefore, resistance corresponding to C point, you will get V upon I 12.63 upon I is 9.2. So you will get 1.373 ohm. Is the answer. Let us see the next problem, second last problem. So in this, a boost converter is connected in middle, and you have to find the duty ratio such that it will operate at MPP. So we have seen the last problem, this terminal voltage. This one is for MPPT point. This terminal voltage is 18 volt. So this terminal voltage is 18 volt and current rating is 11 ampere. So these are ideal converters. So input equal to output. So 11 into 18 volt. So it will give you 198 watt. And we have to find the duty cycle. So let us take it as V naught and this is I naught. So how you can find the duty cycle? So we can write one equation V naught equal to VV plus. So let us take this as IV plus IV RV. So V naught is 11 plus IV RV is 0.02. So let us assume this is first equation. So how you can write V naught into IV? So V naught into IV is also 198 watt. So this is the second equation. So from first and second, you will get IV equal to 14.288 ampere. Two value you will get minus 69 you will also get, but it is not feasible. So it is this one is, so you will get V naught as 13.8576 volt. So therefore, you can find duty ratio. So from here, you will get duty ratio 0.2062 or 20.62%. So this is all for today's session. If you are having any doubt, you can ask me. In the final exam, how to identify which one is multiple choice question. So it is quite simple. They will give you this bracket shape. This is square means in exam, if your options are given in this circular form, then it is single choice. And if the options are given in this square type, then it is multiple choice. Right? And it is written above also, but from the option you can also identify. Chidambaram, it is okay. How to get IPV? It is quite easy. Means in this problem, it is given that this equation is a straight line. So if you know the equation of a straight line and this one point corresponding to C, you will also know. So this point you also know. Means IC you are knowing because it is coming from this equation. So you have to find one point only, VC. So this is known. And from this straight line equation, you can get a straight line equation from these 2 points. Then you can easily find VC. So it is very simple. And IC you are getting from this relation, right? Any other thing you want to ask? If nothing is there, then we will meet on the next session at the same time. Thank you all for joining the session and good night.